Hi everyone, welcome to Unit 5 of online course on probability distributions. Already we defined binomial distribution and its probability density function and its applications in the last module. Now we are going to find moments of binomial distribution. That means mean, variance, third moment, fourth moment, etc. so as to find measure of skewness, measure of kurtosis, etc. for the binomial distribution, and the properties of the binomial distribution can be identified on the basis of these moments. So, we are finding the mean of the binomial distribution. Suppose X is a binomial random variable with parameters n and p, then mean and variance are given by np and npq respectively, and that is the derivation of mean and variance of the binomial distribution I am going to discuss here. Suppose X is a binomial random variable with parameters n and p, and hence our probability mass function fx is equal to ncx p power x q power n minus x, where x is having the values 0, 1, 2, 3, etc. up to n, and p and q satisfying the relation p plus q is equal to 1. Then mean or expectation of x is given by the formula. Since x is a discrete random variable, by definition of expectation of x, this is equal to sigma over x, x into f of x. Then that is equal to, when we are substituting the value of f of x, this is sigma over x is equal to 0 to n x into ncx p power x q power n minus x. Then what we are doing here, this is same as sigma x is equal to 0 to n x into this ncx is written as n factorial divided by n minus x factorial into x factorial p power x q power n minus x. So that is this x and x factorial, so common factors are cancelling. This is same as n factorial divided by n minus x factorial into x minus 1 factorial p power x q power n minus x. The x from x factorial you cancel, then this become x minus 1 factorial, and that is equal to sigma over x is equal to 0 to n minus 1 factorial divided by n minus x factorial. You can write this n minus x factorial as n minus 1 minus x minus 1 factorial into x minus 1 factorial, and p power x, let it be written as p into p power x minus 1. Again q power n minus x is written as n minus 1 x minus 1. So from here you take this n is here written as n. So, n p, that is this factorial and this factor is taken outside, sigma x is equal to 0 to n. This is nothing but n minus 1 c x minus 1 p power x minus 1 q power n minus 1 minus x minus 1. So, that is nothing but our np into this expression is actually q plus p power n minus 1, and that is same as np into q plus p is 1. So, this is np. So, this is the way we are establishing that mean of the binomial random variable with the parameters n and p as np. So, remember, if x is a binomial random variable with the parameter n and p, mean is equal to np. Similarly, we are finding the variance. So, to find the variance, we need expectation of x square first. And what the expectation of x square is obtained by definition, this is sigma over x square into fx. So, we are finding the expectation of x square, and the procedure for finding the expectation of x square or expectation of x cubed or expectation of x power 4 is you make the x square as a linear factors, like x square can be written as x into x minus 1 plus x. So, change the x square as x into x minus 1 plus x. So, then expectation of x square is equal to sigma over x into x minus 1 plus x into fx, and fx, you write, this is ncx p power x q power n minus x. So, instead of this x square factor, we are writing x square as x into x minus 1 plus x. And simplifying or make this as two terms, you have sigma over x into x minus 1 ncx p power x q power n minus x plus second term sigma over x into ncx p power x q power n minus x. So, starting from expectation of x square definition, we arrived this expression sigma over x into x minus 1 ncx p power x q power n minus x plus the second factor sigma over x ncx p power x q power n minus x. Using the same argument we have given in the when we are finding expectation of x, this expression can be written as n into n minus 1 p square sigma over x n minus 2 c x minus 2 p power x minus 2 q power n minus 2 minus x minus 2, the first expression, plus the second expression is nothing but our expectation of x. So, that already we have calculated as np. So, expectation of x square is equal to n into n minus 1 p square, this expression, plus the expectation of x, that is np. So, this is actually n into n minus 1 p square. This summation is nothing but our q plus p all power n minus 2 plus np. and that is n into n minus 1 p square plus np. Why? Because this q plus p is equal to 1. Because q plus p is equal to 1, this value is equal. So, this is our expectation of x square. So, second arbitrary moment, expectation of x square of a binomial random variable is n into n minus 1 p square plus np. Now, we are in a position to find the variance of x. Variance of x, suppose x is a binomial random variable, then variance of x, you know the definition of variance of x as expectation of x square minus expectation of x the whole square. And we calculated these values earlier as n into n minus 1 p square plus np, that is our expectation of x square, minus expectation of x already we have calculated as np the whole square, and that is same as n square p square minus np square plus np minus n square p square, or that is equal to np minus np square, and that is equal to np into 1 minus p, or that is npq. So, remember, if x is a binomial random variable with parameters n and p, our variance of x is npq. So, variance of x is equal to npq, and earlier we have discussed the mean of the binomial random variable, that is mean of x is equal to np. So, these are the two important quantities we derived corresponding to binomial distribution, that is if x is a binomial random variable, expectation of x is equal to np and variance of x is equal to npq. From these two expressions, it is very evident that for a binomial distribution, variance is less than the mean. So, this is a characterization, this is one of the properties of the binomial distribution, that is variance of x is equal to, variance of x is less than expectation of x. Because this can be established, variance of variance of x divided by expectation of x. Suppose you are finding this is npq divided by np, that is q, and q is a value that is less than 1. So, variance of x is less than expectation of x. So, for every binomial distribution, this variance is less than expectation of x. Now, we are finding the third arbitrary moment. Third arbitrary moment, that is equal to expectation of x cubed. And by formula, this is sigma over x, x cubed into fx. And to get the third arbitrary moment, here also we are representing this x cubed as, you can represent x cubed as x into x minus 1 into x minus 2 plus 3x into x minus 1 plus x. So, we can factorize this, the x cubed factor, that as x into x minus, that is a linear combination of these factors. So, x cubed is equal to x into x minus 1, x minus 2 plus 3x into x minus 1 plus x. So that is expectation of x cubed is equal to sigma over x. Instead of this x cubed, you are writing this x into x minus 1 into x minus 2 plus 3x into x minus 1 plus x, that is our x cubed, into fx. Fx is our ncx p power x q power n minus x. And by the same argument we adopted in the case of derivation of expectation of x square and expectation of x, this can be written as n into n minus 1 into n minus 2 p cubed plus 3n into n minus 1 p square plus np. That is, we can derive the expectation of x cubed as n into n minus 1 n minus 2 p cubed plus 3n into n minus 1 p square plus np. Similarly, expectation of x power 4, the fourth arbitrary moment of binomial distribution. That fourth arbitrary moment of the binomial distribution is obtained by sum over x power 4 fx. Remember, this x power 4 can be written as x into x minus 1 into x minus 2 into x minus 3 plus 6x into x minus 1 into x minus 2 plus 7x into x minus 1 plus x. That is, we are representing x power 4 as x into x minus 1, x minus 2, x minus 3 plus 6x into x minus 1, x minus 2 plus 7x into x minus 1 plus x. You can write x power 4 as like this. Substituting this, you can have the value of expectation of x power 4. Expectation of x power 4 is equal to sigma over x, this expression. Instead of x power 4, you are writing the value here, that is x into x minus 1, x minus 2, x minus 3 plus 6x into x minus 1, x minus 2 plus 7x into x minus 1 plus x into fx ncx p power x q power n minus x. Okay, then we have four factors: sum of first term, second term, third term and fourth term into ncx p power x q power n minus x. Then this is simplified, and expectation of x power 4 is equal to n into n minus 1, n minus 2, n minus 3 p power 4 plus 6n into n minus 1, n minus 2 p cubed plus 7n into n minus 1 p square plus np. From this four moments, arbitrary moments, we are in a position to find the center moments also. So, to find the center moments, we have the mu2 already we calculated, that is our variance, and that is equal to mu2 dash minus mu1 dash the whole square. Remember, our mu r dash is expectation of x power r. So, this is our rth arbitrary moment. Mu r dash is equal to expectation of x power r, and mu r is our central moment, rth central moment, and that is obtained by expectation of x minus expectation of x all power r. mu r is equal to expectation of x minus expectation of x power r, and mu r dash is equal to expectation of x power r. And the relationship between mu r and mu r dash, from that relationship we can establish mu 2 as mu 2 dash minus mu 1 dash all square, and this simplify this expression, these values are substituted, n into n minus 1 p square plus np, that is our mu 2 dash, mu 1 dash we have np whole square. This is simplified, already we have calculated as npq. This is our mu 2, that is already we calculated. And mu 3 dash, third arbitrary moment, sorry mu 3, the third central moment, is equal to mu 3 dash minus 3 mu 2 dash mu 1 dash plus 2 mu 1 dash all cubed. This is a relationship between third central moment and the first three arbitrary moments. Substituting, our value become, simplification on simplification, we have npq into q minus p. All these values we calculated. This is our expectation of x cubed, and this is expectation of x square in the expectation of x. These values are substituted, and on simplification we will get the value mu 3 is equal to npq into q minus p. Similarly, you can calculate the mu 4 value, and that mu 4 value is obtained by 3 n square p square q square plus npq into 1 minus 6 pq, and this is also obtained by substituting expectation of x square, expectation of x cubed, expectation of x power 4 in the recurrence relationship, sorry, the formula between center moments and arbitrary moments. Our simplified expression become mu 4 is equal to 3 n square p square q square plus npq into 1 minus 6 pq. So, for a binomial distribution, after getting the first 4 arbitrary moments, that is expectation of x square, expectation of x cubed, and expectation of x power 4, using the relationship between arbitrary moments and center moments, we can find mu 2 as already we calculated variance, and mu 3 as npq into q minus p, and mu 4 as npq into 1 plus 3 n minus 2 pq, or we can write this expression as 3 n square p square q square plus npq into 1 minus 6 pq. This way also we can write this expression. So, these are the first 4 center moments of the binomial distribution. Before concluding this session, let us consider some examples. So, suppose x is a binomial random variable with 6 and 1 by 3. If it is, we have the f of x as 6cx 1 by 3 power x and 2 by 3 6 minus x, where x is equal to 0, 1, 2 up to 6. So, this is the probability mass function for this particular random variable. Suppose the question is, what is the mean and what is the variance of the binomial random variable? Instead of finding the mean and variance using the definition, it is possible to find the mean and variance using the expression that we derived. That is, mean is equal to, for a binomial random variable, mean is equal to np and variance of x is equal to npq. Hence, for this expectation of x is mean is equal to 6 into 1 by 3, that is 2, and variance of x is equal to, that is equal to 6 into 1 by 3 into 2 by 3, that is 4 by 3. So, mean is equal to 2 and variance is equal to 4 by 3. So, that is, we are without using the general definition of the expectation of x and variance of x, using the expression that we derived for the binomial random variable, we are calculating the mean and variance, and that is 2 and 4 by 3 respectively, because mean is equal to NP and variance of NPQ, that is our expression for the mean and variance of the binomial distribution. And with this we are wind up this session, and we will discuss the moment generative function and other recurrence relationship between the center moments, etc. in the next session. So, thank you for listening this session. Thank you.